Okay, so math counts week 10, we're doing quadrilaterals. The topics are the quadrilateral family tree. We're going to do more in depth on trapezoids and parallelograms. We're going to do some similar triangles in quadrilaterals and then math counts problems. Okay, so this is the quadrilateral family tree. So if you know a regular family tree, it's basically you have the ancestors and their children. So basically what this family tree is that all quadrilaterals are related. They're like a big family. So so we have the great grandpa, which is just the quadrilateral. And this means this family tree says that all the quadrilaterals below this great grandpa is going to have the traits of this grandpa. So let's say we take the rhombus here. The rhombus is the child of the parallelogram and the kite. So it has all these aspects of a kite, all these aspects of a parallelogram. And a parallelogram is a trapezoid. So it has all the aspects of a trapezoid. And it has all the aspects of a quadrilateral. So every single quadrilateral down the line here is going to have all the traits of its ancestors. So the square has the traits of everything, okay? A square, I didn't write any traits here because it has all of these things, okay? So this is basically the quadrilateral family tree. I would recommend you take a screenshot of this. Save it to your camera roll. Not sure if you have any trouble seeing this. Let me hide the video panel. Okay, so I hope you can see that now. So this is the quadrilateral family tree. So take a screenshot, whatever you want. Give me a moment to do that. This is kind of like a review sheet for quadrilaterals. It doesn't really give you everything about each of these quadrilaterals, but it's a pretty good review sheet you can use, okay? All right, so let's go. So today we're not gonna do the kite or the rhombus or the square and stuff. Today we're only going to be focusing on the trapezoids and the parallelograms, okay? Because usually these are the ones that are hardest, and these are like the ancestors, right? So you can apply the properties of these shapes to the square and the rectangle and the rhombus. So yeah, so like if you learn this, then you will inevitably learn more about the rectangles as well. But if you do want to learn more about the other specific shapes like the kite that I'm not going to cover today, I have a video on all the quadrilaterals in the family tree on my YouTube channel. So I'll send you guys that link later if you want to check that out. But today we're only going to focus on trapezoids and parallelograms. So first of all, what's a trapezoid? A trapezoid is if we take two parallel segments and connect them like this, we get a trapezoid. So a trapezoid has one pair of parallel sides. Okay? At least one pair. So this means that if the trapezoid would have two pairs, that would still be a trapezoid. It would just be a parallelogram then. So a parallelogram is a trapezoid. So what can we get from this aspect of a trapezoid? This is the only thing that can make a trapezoid a trapezoid. So what properties does it have as a result of this? Well, we know that when we have parallel lines going through a transversal, we get some congruent angles and supplementary angles. This angle will be supplementary to this one, right? Because this angle will be congruent to this one, which means that they're supplementary. So what this means is that these two angles are supplementary. These two angles are also supplementary because we have another parallel line, two parallel lines with a transversal. Okay, so these two are also supplementary. Okay, so basically the angles, the adjacent angles, which means they're next to each other, the adjacent angles on the non-parallel sides are supplementary to each other, okay? So this is a relationship between the angles of a trapezoid. One thing is that there is no relationship between these, okay? Only the angles adjacent along the sides that are not parallel are supplementary, okay? So what else do we have from a trapezoid? Well, let's draw it again. Drawing the diagonals of a trapezoid, which means we're connecting the opposite vertices. Okay, so you can see that we've made 4 triangles here. Not really 4 triangles. We actually have even more triangles than that. But you can see that these triangles, this triangle and this triangle, are going to be similar. Because again, we have this transversal and parallel lines, right? So if we take this transversal, let me use red here. If we have this transversal, this angle is the same as this angle, right? Because we can see the parallel lines and the transversal. If we take the other transversal right here, then this angle is congruent to this angle, right? And now you can see that if we have this triangle, and this triangle, they're similar because they have 2 angles that are congruent, which means they're similar by angle-angle similarity. So these are the 2 similar triangles you can make by drawing the diagonals of a trapezoid. Does everyone understand this? Well, okay. So these are the 2 similar triangles. The other 2 triangles you make are not similar, okay? They're not necessarily similar. This one and this one, not similar, okay? It's only the ones that are made with the parallel sides, because only if these are parallel, we can make sure that these angles are going to be congruent, okay? So now let's go on to the area of a trapezoid. The area, we're going to have 2 bases, base 1 and base 2. And the bases are basically the parallel sides, the lengths of the parallel sides, and the area is going to be the average of the bases. So to find that, we're going to have to add them and divide by 2. That's the average. And multiply that by the height, and the height is this. So that's the area of a trapezoid, okay? This kind of makes sense because if you were to cut this triangle out of the trapezoid and put it here, and cut this triangle out of the trapezoid and put it here, then we're going to have a rectangle, right? And you can see that the side lengths of these rectangles, they're probably going to be the average of the bases, okay? So that's how it works. The average of the bases times the height. That's the area of a trapezoid, okay? So that's all you need to know about trapezoids. Now let's go on to parallelograms. Parallelograms, that means we have 2 parallel sides, 2 sets of parallel sides, which also means that it's still a trapezoid. So it has all the properties of a trapezoid. So what this means is that these 2 angles are going to be supplementary, right? Because it's still a trapezoid, and these 2 lines are parallel. You can see that if we have a transversal like this, they will be supplementary, which means that these 2 are also supplementary. But if we look at the other parallel sides here, these 2 lines are parallel, which means this can also be a transversal, which means that these 2 angles are supplementary, which means that these 2 angles are supplementary. So in a parallelogram, adjacent angles, which means the angles that are next to each other, are going to be supplementary. Okay? So if this angle is x, this is 180 minus x. 180 minus x is supplementary to this. So this angle is going to be 180 minus 180 minus x, which is going to be x. So as you can see here, the opposite angles are congruent. Okay, so opposite angles are going to be congruent. Okay, so those are the relationships between the angles in a parallelogram. Adjacent angles are supplementary and opposite angles are congruent. So this means this angle is congruent to this angle as well. Okay, so now we're going to go on to the diagonals of a parallelogram. What do we know from those? diagonals, if we draw them in, they actually bisect each other. So what this means, remember when I said bisect? Angle bisector means it cuts an angle in half. So these lines are going to bisect each other, which means they're cutting each other in half. Okay, so this is congruent to this. This is congruent to this. Okay, so that's a really important aspect of a parallelogram. And I'd say a lot of the problems involving parallelograms is going to involve some kind of diagonals intersecting, and you're going to have to know that the diagonals bisect each other. Okay. Now we can have when we have the diagonals, we can draw in, we have 4 triangles, okay? And all 4 of these triangles have equal area. Which means that each triangle is 1/4 the area of the original parallelogram. Okay? So what else is there? So actually, these 2 triangles are going to be congruent. Let me draw it in with a different color. These 2 triangles are congruent, which means they're the exact same, right? Because right here we have the exact same different lengths of sides. And right here, we have congruent angles. So these 2 triangles are congruent, and another pair of congruent triangles are these 2. The blue triangles are congruent. Okay? So for a parallelogram, the area of the parallelogram is going to be the base times the perpendicular distance between the bases, which is the height. Okay? This length is not the height because it is not perpendicular to the base. Okay? The height has to be the perpendicular distance between the bases. So this is base 1. We could have the other base. We could set this as the base. And if we want to set this as the base, we're going to have to use a different height. It's going to be this, the perpendicular distance between those 2 bases, okay? So 2 ways we can find the area of a parallelogram. So let's do some problems here. We have around 5 minutes for these. So these might be a little challenging. That's okay. Okay, so I'm going to go through the solutions now. So the first one, I want to find the area of this trapezoid. So what we'll need is the bases and the height. So how do we find those numbers? Well, we see 120 degrees. It's got to be useful somehow, right? So since we know that's true, this is going to be 60 degrees because those angles are supplementary, right? That's 60 degrees. When I think of 60 degrees, what do I think of? I think of a 30, 60, 90 right triangle. How do I make a 30, 60, 90 right triangle? We've got to make a right angle somehow, right? So I'm going to draw a line down to be perpendicular. So now I've got a 30, 60, 90 right triangle. And you can see how using this triangle, I can find the height. Okay, so using this triangle, 6, this will be 3, this will be 3 times the square root of 3, which means this is also 3 square root of 3. It's also the height, right? The height is the same through the whole trapezoid. If this is 3 root 3, that's 5 root 3. That reminds me of a 3, 4, 5 right triangle. You could use the Pythagorean theorem, that would work, but I'll just use a shortcut here. Since this is 3 root 3, 5 root 3, this will be 4 root 3. Okay. Now to find the other base. We got the height, we got to find the other base now. Well, that's just 20, subtracted the 3, subtract the 4 root 3. This is going to be 17 minus 4 root 3. Okay, so then the area is going to be this plus this divided by 2 times 3 root 3. So this is going to be okay. So and if you were to evaluate that, you would get your answer. All right. So now the next one, we're going to use a very similar strategy. First, we got to use this clue here. AB equals BC equals CD equals 1. So AB is 1, BC is 1, CD is 1. Okay, now I want to find CA. Well, we got to draw this in somehow, right? So let's draw it in. Again, we have 120 degrees. What does this mean? Well, if you were to think about this, we're going to think about, right here, we thought about 30, 60, 90 right triangles, right? So here we're going to think about it as well. So this is what we call an isosceles trapezoid, because these two sides are the same. Okay, and in an isosceles trapezoid, these two angles are the same. Okay, because if you think about it, it's basically a mirror. It's a mirror reflected around here. Okay, so by symmetry, we know that this is 120 degrees. So now I've got this triangle here. It's an isosceles triangle with CA as the base, with sides of 1 separated by 120 degrees. So what we can do now is we can drop a perpendicular line here to separate this 120 degrees into 60 and 60. 30, 60, 90 right triangles, right? So this is going to be 1/2. This side is going to be root 3 over 2. This is going to be root 3 over 2. So CA is those two things added together. We will have just root 3, and that will be the answer. Any questions about these? Cool. So let's go into these two problems, these three problems about parallelograms. And all of these problems are referring to that diagram on the right, okay? I'll give you 3 minutes for these. All right, so for the first problem, we're going to find AC. So AC is going to be this line right here. Let me first turn on annotations. This is what we want, right? Well, we know that AC is bisected by BD, right? So if we can find what this is, we just multiply what this is by 2 to get AC, right? So how to find this length? Well, we can use the triangle here. This triangle area is going to be 6 times 3 divided by 2. And remember, no matter what combination of bases and heights we use to find the area of a triangle, we'll get the same answer. As you can see here, 2 is the height to the base right here. So this is also equal to 2 times whatever, let's say it was x. So x is down here, divided by 2. So and if you solve this, you'll find that x equals 9. So this will equal 9. Right here, this is 9. So the whole thing, AC, is going to be 2 times 9, which is 18. Okay? So now we're going to do the next part. Find the area of ABCD. We already know the area of the small triangle right here, right? This triangle has area 6 times 3 divided by 2, which is just 9. Right? The area is 9. And we know that each triangle made by these parallelograms is going to have the same area. Each of them is having 1/4 of the area of the whole parallelogram. So to find the area of the parallelogram, we just multiply 9 by 4. So that will be 36. Okay? So finally, if P is on AB such that PD is perpendicular to AB, what is PD? So we have to have a point P here so that PD is perpendicular to AB, okay? Well, if you look at this, this is just the height of the parallelogram. We know that the area is 36, and we know the base to this height is going to be 6. So 36 is 6 times the height, which is going to make the height equal to 6, and that's the answer. PD is 6. Any questions about these? Cool. Now we're going to go over similar triangles in quadrilaterals, okay? Well, we already know some similar triangles. We know that if we have a trapezoid here, let me draw the diagonals. These two triangles are similar, okay, by angle. It's not just trapezoids. We also have parallelograms, right? Parallelograms, they go a step further. These are congruent triangles, but similarly, congruent triangles are also similar to each other, right? They just have the factor between them. The dilation factor is equal to 1. Okay, so congruent triangles are technically similar triangles as well. But if we see in rectangles, we have a rectangle here. A rectangle, if we look back in the family tree, if you look at that on your screenshot there, if we draw the diagonals in here as well, they're going to be similar. This is going to be similar to this. Because a rectangle is a trapezoid. It is just a more specific type of trapezoid. Okay? And sometimes, some problems, you're going to see a rectangle, and they're going to look like this. Okay? So when you see this type of problem, this is actually a common type of problem. They're going to draw a diagonal, and they're going to draw a not as, it doesn't go all the way to the corner. It just goes like halfway maybe. So to find lengths in these triangles, sometimes you're going to have to draw your own triangles in, okay? So sometimes you're going to have to draw in a perpendicular line here to make similar triangles, okay? Sometimes when you just look at the diagram, the similar triangles are not all given to you yet. So sometimes you're going to have to look at it and draw in lines. So if I drew that line in, I now have a new set of similar triangles that I can use to solve for my answer. Okay, so sometimes you're going to have to draw in lines to make new similar triangles to find what you need. Okay, so that's more like a problem-solving technique. Oops. So let's do these. First one, you just apply the similar triangles in the trapezoid. All right, so for these problems, first we have in trapezoid ABCD, BD is 13. So this means that if this is 3, this is 10. Okay. What is the ratio of AB to CD? Well, we know that if we label this as E, ABE is similar, ABE right here is similar to CDE. Okay, and this symbol means they're similar. Okay, so if this is true, then the ratios of the corresponding sides are equal. So the ratio of BE to DE, which is 3 to 10, is the same thing as AB to CD. Okay, so it's just going to be 3 over 10. Okay, and the next one, we're going to have a parallelogram ABCD. We're going to have to draw this in. A, B, C, D. They intersect at E. Diagonals intersect at E. That's not a terrible drawing. E. Okay, so now ABCD has area 12. If F is the midpoint of AE, HG is the midpoint of BE, H here, L here. We have a new parallelogram down here. What is the area of FGHL? Well, we have similar triangles here. This triangle, notice here, this triangle is similar to this triangle, right? Because they have parallel lines, which means this angle is congruent to this angle is congruent to this angle, which means they're similar by AA similarity. Okay, so now F is the midpoint of AE, G is the midpoint of BE. So this means that the ratio of corresponding sides is 1 to 2 in these two triangles, right? So this will be 1/2 of the original base. Let's say this was the base, this will be 1/2 of the base. If we do the same thing for all the sides here, every single side is half of the original length of the sides of the original parallelogram. So this was A and B and A and B. All the sides are 1/2 of the original. So what does this mean about the area, the ratio of the areas? Well, area is base times height, right? We know the base has been shrunk by 1/2. The height has also been shrunk by 1/2 because the entire parallelogram has been shrunk by 1/2. So the height is also shrunk by 1/2. So it's going to be 1/2 B times 1/2 H. So the area of the new parallelogram is going to be 1/4 B times H. The area of the original was B times H. This was 1/4. So it's 1/4 of the original area. So the area is going to be 12 divided by 4, 3. Okay? Any questions about these? Cool. I'm going to do some Mathcounts problems. I labeled these as Mathcounts level problems. This one is actually a problem from Mathcounts competition. So I'll give you 5 minutes for this one. All right, so for this problem, we got to draw a diagram, right? If you don't draw a diagram, I don't know how you're going to do this. We're going to have a parallelogram A, B, C, D. The diagonals are going to intersect at E. Point F is the midpoint of BE. H is the midpoint of CE. What is the ratio of AFHD? So let me draw this in with a different color. AFHD. This shape. What's the area of this to the area of the parallelogram? What's the ratio? So first of all, what even is this shape here? Well, it's a trapezoid, right? Because these lines are going to be similar. These lines are parallel. These lines are parallel, so they're all going to be parallel. It's a trapezoid. So if we can find the bases and the height in relation to the length of the sides here, then we'll find the area of the trapezoid. Okay. So let's say this is base. We have the height here. Let's do it like this. So this is the height. This is the height. Okay. So we know the area of the parallelogram is going to be base times height. So what about the area of the trapezoid? Well, we already have one of the bases. Now we got to find this one. What's the length of this? Well, since these two triangles are similar, this triangle is similar to this triangle, right? And since F is the midpoint of EB, which means that this is 1/2 the length of this, of BE. EF is 1/2 the length of BE. EH is 1/2 the length of EC. So this means by similar triangles, the ratio of corresponding sides are equal. So if this is also the base, right? Because it's the opposite side of the parallelogram. This will be 1/2 times B, okay? Because the ratio of corresponding sides are equal. So we know the bases of the trapezoid now. Now all you gotta do is find the height. Well, if we know this, the height is made up of these two sections here. Let me clear up this a little bit. Here, okay. Clear it up a little more. Okay, so the height of the trapezoid is made up of these two sections. This section is going to be 1/2 the height because it goes from the base to the midpoint, the middle right here. Okay, so that's 1/2. The other section, well, again, based on similar triangles, this triangle is similar to this triangle. The height of EBC is going to be 1/2 H. If this is H, then the height of EBC will be 1/2 H, which means that the height of EFH will be 1/2 H times 1/2, because this triangle is 1/2 of EBC. Okay, so this section is going to be 1/4 H. So the actual height of the trapezoid is going to be 1/2 plus 1/4, 3/4 H. Okay, so now we really have all we need, because the area of the trapezoid is going to be the average of the bases. So it's going to be B plus B over 2, so that's the average, times the height, which is 3/4 H. We just do a little simplifying here. We can factor out the B out of here. If we factor out the B, that will be B, 1 plus 1/2, which is 3/2 over 2 times 3/4. 9 over 16 B times H. That's the area of the quadrilateral AFHD. So the ratio will be this divided by the original area of the parallelogram. So it's just going to be 9/16. That is the answer. Any questions about this? Well, so I do have more Mathcounts problems prepared. Since we're out of time, I'll just put those in the homework. Okay? So that will be it for today. I'll see you guys next week. Bye.
Bye.
Bye. Change my name here.